Welcome to our journey into quantum linear algebra for beginners. Get ready to dive into the fascinating world where quantum mechanics and linear algebra intertwine. Quantum linear algebra is a branch of mathematics that combines the principles of linear algebra with the concepts of quantum mechanics. It provides a mathematical framework for understanding and manipulating quantum systems, where properties like superposition and entanglement come into play. Quantum linear algebra is essential for understanding quantum computing, quantum information theory, and quantum cryptography. Let's start with some basic concepts. In quantum linear algebra, we deal with quantum states, which are represented by vectors in a complex vector space known as Hilbert space. Qubits, the fundamental units of quantum information, are represented as vectors in a two-dimensional Hilbert space. Quantum operators are represented by matrices, and they act on quantum states to transform them. Tensor products allow us to combine multiple quantum systems into larger composite systems. Quantum linear transformations describe how quantum states evolve over time. Quantum gates are fundamental building blocks of quantum circuits, and they are represented by unitary matrices. Unitary transformations preserve the inner product between quantum states. Entanglement, a unique feature of quantum systems, is described mathematically using quantum linear algebra. Quantum linear algebra has applications in various fields, including quantum computing, quantum information theory, and quantum cryptography. In quantum computing, quantum linear algebra provides the foundation for designing and analyzing quantum algorithms. Quantum information theory studies the properties of quantum information, such as entanglement and quantum communication. Quantum cryptography utilizes quantum linear algebra to develop secure communication protocols. As we conclude, remember that quantum linear algebra is a rapidly developing field with potential for groundbreaking discoveries. Key concepts we covered include quantum states, operators, and entanglement. These concepts form the basis for understanding quantum linear algebra. Challenges in future directions include developing efficient quantum algorithms and exploring quantum gravity. Let's stay curious and continue our exploration of quantum linear algebra.